All right, so what we're going to talk about today are, let's see, later, remind me tomorrow. What we're going to talk about today are tangent planes. Okay, so first off, let's just go back to Calc 1 for a minute, or earlier this semester. Right? Just that. So how did I get that? Well, basically, what have I done? It's a point slope kind of thing, right? Yes? Okay, so what we want to do is sort of investigate what's the multivariable analog of this. Okay, so what if I had some curve, what would this look like if I drew the tangent object? There he is. Poor K. Who's that Plutard? Oh, no, thank you. Can stop there. uh, yeah. I do have this for you, however. Well, yeah, but this way you can see it. Right. Yes. Okay. So, right. So, got a tangent, pick a point, draw the tangent line, right? No big deal. Okay. So, what we want to do is, to quote Emerald, right, we want to kick this up a notch and look at what would the idea of tangency be if we're now talking about surfaces in 3 dimensions. Okay. So, new. Okay. So, first off, does it make sense that if a line can be tangent to a curve, if I kick up to a surface, what would be the object that's sort of replacing the idea of line here? Okay, so what's like a two-dimensional line, if you will? A plane, okay, a flat plane, okay? So we need to cook up the equation of a plane. Now, a plane would have an equation that looks something like that, okay? So here I've written it in the form z minus z naught equals something x minus x naught and something y minus y naught, okay? First off, do you guys abide that that kind of looks like the equation of a line, but now we've got 3 variables instead of 2, okay? It's a linear equation with 3 variables instead of 2. Okay, does that make sense? All right, so the question that we want to answer is what are m and n, right? So those numbers out front are going to be kind of like slope thingies, right? So in the same way that in the multivariable, or sorry, the single variable context, what was the coefficient? What was the slope of my line? It was given by the derivative, okay? Well, a plane, in a sense, really has 2 slopes, right? It has a slope in the x direction, and it has a slope in the y direction, and those can be independently adjusted from each other to make the plane slope. And, you know, kind of, those of you who are online can't see me doing like dancing, right? Yeah. No? Okay. All right. So, um, right. So the question then is if m and n are going to control sort of the slope in the x or the y direction, in terms of the function f, what gives us those slopes, those numbers? Well, what do you think? What's your spidey sense tell you? How about some partial derivatives, right? And lo and behold, how many partial derivatives do we have if the function depends on two variables? We have exactly two, right? One for the x direction and one for the y direction. That's in, or Beyonce, excuse me. This help if I say the right things in Chinese, right? Not see ya. My bad. Yeah. Well, I could say the other two phrases I know, but right, those are naughty. I forget who taught them to me. Taught me a couple of Chinese curse phrases. So just, for fun, right? Okay, so the partial derivatives. And when we say the partial derivatives, we have to remember to actually plug in the particular point that we're at. So in the same way that in the Calc 1 context, we didn't put f prime of x in front, we put f prime of a, right? So f, the derivative at the specific point that we were going to be tangent at. Same thing here. We need to plug in specific points. Okay, so notation. Okay, so when we wrote the partial derivatives, we wrote them in Leibniz style, which is the thing on the right. So it looks like df dx, but with sort of the funny d. Yes? Okay. And if I want to plug in a specific value to that, then I could use the little vertical bar. Okay. Another very common way to notate this is the thing on the left, f sub x of x naught y naught. Okay, so the meaning there is f sub x, what have you done? You've taken the derivative with respect to x. And similarly, I could talk about f sub y. Okay, and if I have multiple letters there, so like what's f sub xx? Yeah, it'd be the second derivative with respect to x. F sub xy would be derivative with respect to y and then with respect to x, because remember the order is backwards. Uh, but an f sub yx would be with respect to x first and then y. Now, is there any difference between those two? Usually no, right? For nice functions, they're the same. And basically, for y'all's purposes, all functions are nice. Okay. Yeah, you're welcome. It's my Christmas gift to you. Okay. So, our tangent plane, and that is the worst looking word, tangent, I've ever written in my life. Okay, is going to be this, right? So the slope in the x direction is given by the partial with respect to x, and the slope in the y direction is the partial with respect to y, and then that's it. Okay. All right. Now, if I want to graph this thing or graph the surface, what's one thing I can do? Can I just take this term and move him to the other side? Sure. Okay. And so then I have this as an actual function. And then I'll just copy and paste this because I'm lazy. Okay. So all I've done there is move the f of x naught y naught to the other side so that now I have it as an actual function in the form z equals. Okay, that's not necessary, but it will be useful for something that we'll do a little bit later today, so might as well just do that now. Okay, so does that kind of make sense? how we've analogized up from single variable to multivariable, well, two variable in this case. Yeah? Okay, so now let's look at what this looks like. Okay. All right. So over to Mathematica and Cole's favorite part of class. Oh yeah. Cole wants me to do like a ASMR Mathematica channel. What does ASMR stand for anyway? Yeah. Okay. All right. So first off, we need to pick an equation for or function for a surface, right? So let's just do something. Let me pick this, which I think we've seen before. This is the top half of a sphere. Okay. Um, and then I could plot it, right, with plot 3D. Right, and I'll just plot this from -2 to 2, even though I don't really need to. And it will take forever to run for some squirrely reason. There it goes. Okay, so, all right, so it looks a little bit lopsided because what I need to do is, oops, that was too much. Well, here, let me do 0 to 2. Why does that look so dang flat? Oh, no, I want to do -2 to 2. Why is this looking, why from -2 to 2? Oh, yeah, that's why. Okay. Because I'm being a bonehead. There we go. Still a little flat, but okay, whatever. You guys get the idea, right? Okay, so top of a sphere, great. Um, so um, now I want to pick a point on it. Okay, now for demonstration's sake, let's start with probably the silliest possible point on this thing, which would be where? Well, to find a tangent plane, one that's really easy, where hopefully the answer will be obvious. At the very top, okay? At the very top of the hemisphere, what should the tangent plane be? Horizontal, okay, in the sense that it'll be parallel to the xy plane, and it will touch the top of the sphere, right? So if we're right at the north pole of the sphere, if you will, then what should the equation of the plane be? How about z equals 1, right? Okay, that's easy. And what we want to see is if that's in fact correct. So what I'm going to do is I'm going to define fx to be the derivative with respect to x. Okay, and similarly, I'm going to define fy to be the derivative with respect to y. Okay, what this means is that I can then plug numbers into these functions and get the specific slopes at specific points. Okay, okay, and what was my equation that I had over there? It was that stuff over there. Okay, so I had f of x naught y naught, or sorry, x naught y naught, plus fx of x naught y naught times x minus x naught plus fy at x naught y naught times y minus y naught. Okay, so what I've actually defined here is a 4-variable function. X and y are going to be its variables, and then I need to plug in constants x naught and y naught, and this way I can use that thing for every tangent plane, and I don't have to adjust the equations, okay? And so if we wanted to plot the tangent plane at the North Pole, then I would plot t of xy, comma, 0, 0, right? Because where is the North Pole on the sphere? What's its x and y coordinate? 0 and 0, okay? So does that make sense, sort of the syntax here? And then I'm telling Mathematica the curly braces allow me to plot two things at once. Okay, so what should we see when I execute this? I should see the hemisphere with a flat plane that's horizontal on top of it, if I haven't screwed anything up. And lo and behold, there we go. Okay, and Mathematica draws them, in the same sort of color order, right, or similar. So like the original surface is graphed in orange, and this new one is graphed in sort of this blue color. And yeah, okay, does that make sense? Okay, so that looks good. But what are the values of the partial derivatives at the North Pole? Well, they should be both 0, correct? Well, let's just double check that in fact they are, because what are the derivatives with respect to x and y, right? If I plug 0, comma 0 into those, what do I get? I get 0 over 1, right? So there's no division by 0 here, no worries. Okay, good. And there we go. Okay. All right, so does that make sense for the North Pole? Okay, now obviously that's the only place where, well, for this particular function, where the plane would be horizontal. If I pick some other point, then it's going to be slopey, right? So give me two other x coordinates that aren't 0 and 0. Colin, give me an x coordinate between 0 and 1, say. 0.75. Okay, thank you. Mr. Trapp, give me another one. 0.2. Okay, so yeah, so there we go. We've got the tangent plane, and it's tangent at that point, and it got chopped off a little bit up at the top because it goes outside the viewing window, but there it is, right? What do you mean, what? Oh, it's because I told it explicitly to only plot from 0 to 2, and this plane goes above that, so it's chopped off the top of it just for graphing purposes. I mean, right, because this plane is infinite. It's just I'm only displaying a finite portion of it, and yeah, so that's a graphics thing. Um, yeah, okay, but does that make sense though? Like, and it sure looks tangent to me, right? If I kind of look at it from the side there, yeah, yeah, pretty Gucci, yeah. Okay, well there you go. That's how tangent planes work. Yeah. Okay, so that's pretty cool. That's cool. That's cool. Okay, Kyle, that's yeah. I get to reach these keys. And I need to switch over to my other charger. So it turns out that this dual charger I have can charge my laptop. It can charge one thing at 100 watts or two things at 45 watts each. And when the processor and the graphics card are fully running, this thing needs 100 watts or else the battery starts to slowly drain. So I was experimenting to see how fast I could yeah, if it was able to keep up at 45 watts, and the answer is nope, it's not. So, okay. Anyway, so does that kind of make sense? Yeah. Now, what we can do with this is so again, let's kind of go back to Calc 1, for example. Um, the we can use this to approximate functions. Okay. So, for example, let me take um, two things here. So you guys picked 0.75 and 0.2, right? And f of that is, okay, whatever that number is. Okay, 0.63, blah, 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 blah. Okay, so what is that, right? It's the square root of 1 minus the sum of the squares of the numbers you guys picked. Okay, and now we have Mathematica, right? So it's easy to calculate that. But what would happen if I instead did t of um, t is my tangent plane. Okay, so yeah, I need x and y first. Okay, but so let me put that right. Okay, so if I do that, then I get this thing. Okay, so that's the equation of my tangent plane, right? Z equals that thing. Okay, at the particular point that you guys chose. Okay, so in this case, this is sort of this is a bad example with the particular numbers we've got, but what would happen if I chose a value of x and y that were not exactly 0.75 and 0.2, but close to it? So let's say, for example, I do 0.76 and 0.1. Ah, that's not what I mean. Okay. What I mean is, what would happen if I took 0.76 and plugged it in for x here, right? I'd crunch it and I'd get some number, right? Okay, so here's the question. How do you think t, so let me write it this way. Let's suppose that I want to calculate this, okay? But what I'm going to do instead is use t, okay? Now, what do I get? So the quote true value is this one. If I use my tangent plane equation, what do I get instead? A little bit bigger. Are they close? Yes, they are. Okay, should they be close? Yeah, okay. And so what I've done, right, is I've said, okay, the tangent plane and the function agree perfectly at the point 0.75 comma 0.2. Yes? So if I go a little bit away from that, then they won't agree anymore, but they'll be relatively close together. Okay? The further away I get from the point 0.75 comma 0.2, the worse the approximation gets. Okay? So if I wanted to approximate the function, I can instead use its tangent plane to do it. Okay? Knowing that the answers are going to be relatively close. Okay? Does that kind of make sense? Yeah? Yeah, Jack. Yeah, because what have we defined here? We've actually defined a first order Taylor approximation, but in a multivariable context. Okay, now here's where multivariable stuff gets real icky because, well, what was one of the problems on the assessment yesterday? It was, right, to use a quadratic Taylor expansion to approximate the square root of 2, okay, or whatever, right? Uh, now that we all know what quadratic means. Yeah, okay. So that said, right, if we wanted to, if we did a linear approximation, we would get an approximation, but it would suck. Okay, and so what's the idea of a Taylor series? Well, add on more terms and you'll get more and more accurate approximations, right? Okay, so here we've basically only added on the linear terms, but this time there's two of them, right? Because we've got the x and the y directions to worry about. Okay, how many terms would I need to tack on if I wanted to make this sort of a quadratic approximation? And there's two correct answers to this question. Yeah, sure. Okay, 4 is one of the correct answers. No. Well, okay, what's the slightly smarter answer? 3. okay? Because what would the four extra terms be? With respect to x twice, with respect to y twice, with respect to x and then y, with respect to y and then x. But what do we know about with respect to x and y and x? They're the same, so we could crunch those together, okay? So we could build a quadratic version of this thing, okay? And in fact, let me draw what, or program in what it would be. Okay, so one thing I need to do is I need to do this, but I need three more of them, okay? And I need my second derivatives with respect to x twice, y twice, and then with respect to x and then with respect to y. Okay, then I'm going to define a new function here. Dang it. Bracket equals, okay, which will be the same as t, right? So that gets me all of those terms. And then I'm going to add on fxx of x naught, y naught, times x minus x naught squared, fyy of x naught, y naught. It means with respect to x twice. So I take the second derivative, right? Okay. And then that thing times y minus y naught squared. And then this one's the fun one. Oops. Because it's mixed. It's got, I went in the direction of x once, in the direction of y once, and so I have a mixed term, one x and one y, and then there's two of them because I know that they buddy up, okay? Now, what actually do I need here? What's the one thing I'm missing is all of this stuff needs to be multiplied by what? Huh? Well, think back to the single variable case. What's the quadratic term's coefficient? Second derivative divided by 2 factorial, which is 2, okay? So I may need to divide this thing by something. All right, so let me semicolon that out, and I'm going to replace t with q. Oops, whoa. Oh, that's why. Can't put those here. Okay, and then I think I need my over 2 as part of the problem, so. It's giving me a quadratic approximation. Okay, let me plot them in the other order. So actually, I know what I need to do. Oh, I don't remember what the transparency thing is. Basically, I can make them see-through. So what I've got there is I've got a surface. It's a quadratic surface. Let me plot it by itself. Oops. Okay, so this is my surface that approximates the shape of the sphere, but it's not perfect. Yeah.
What's the deal with like all the jaggedness?
It's not so much jaggedness, it's just because the two surfaces are overlapping, and so it's basically a graphics bug. Yeah, it's just a graphics thing, right? So yeah, so basically what we can do here is we can kick up the idea of a Taylor expansion to a multivariable context. Here we have it quadratic. All right, where this starts to get really nasty, though, is if we wanted to do a cubic version here, how many third derivatives are there? Well, huh. So I could do with respect to x 3 times, with respect to y 3 times, x twice, then y twice, then x, right? There's a bunch of them, right? Like 9 of them, okay? Or by 9, I mean 8, because it's 2 to the third, right? I have two choices for each derivative, either x or y, and 2 to the third is 8, right? Some of them are equal to each other, okay? But, so for example, doing x twice and then y is the same as doing y and then x twice, right? For the same reason that we've said here. But I could do it, it's just I would have a crap load more to type in, okay? Now, let's use my Q approximation here, and let's compute this, dang it, but using the Q approximation, and what do I get? Something that's much closer to the, quote, correct answer. And that shouldn't be a huge shock, right? I used the second derivatives, all four of them, or three of them, depending on how you want to look at it, and ba-bam, right? The top one. Well, it's not so much over under. I mean, it's coincidence that it's over under. Um, well, okay, actually, the reason it's over under is what's the concavity of this surface, the orange surface? It's concave down, right? And since we included a quadratic term that depends on the second derivative, the second derivatives are all negative, right? Which means that we would be the parts that I tacked on actually subtract off something from the t approximation, and therefore I get something smaller than the t approximation. I get the q approximation, which was maybe a little bit too small, but that's okay. Nope, nope, no. Okay, does that kind of make sense though? Right? It's a lot better, right? Here it agrees in the first two decimal places, and it's only off by 1 in the second decimal place, right? So it's much closer. Okay, but it was a crap ton more work to program and find all those coefficients, right? Because, well, I've got 4 or 3, but I've got multiple second derivatives in the same way that I have multiple first derivatives. And doing this for cubics would get even worse. Okay, but does that make sense? Okay, so the linear approximation, meaning the t approximation, t for tangent, is not really all that horrible. Okay, it's not, well, what is it from, I think I've used this one before, the HBO miniseries Chernobyl, right? 3.6 Ronkin, not great, not terrible, right? So our tangent approximation here, not great, also not terrible, okay? And if we wanted to do just a quick approximation of a function, that's good enough, right? If we want to really, really spice this up, though, then we got to do the quadratic one, and that means a lot more work, unfortunately. Okay, is that, excuse me, kind of make sense? No. We? Why are you putting so much emphasis on the age? Yeah, wheat thins. Will Wheaton. Yeah, okay, so does that kind of make sense? Yeah? Good? Okay, so there we go. There's tangent approximations. All right, so what we can kind of do here, though, is let's sort of do a preview of attractions for what we're going to talk about on Monday. Okay, so let me go back up to, let me change my plot here and do the tangent plane again. Okay, and let me actually change my point to 0, 0. Okay, which was the top of the sphere. okay? And that's what we had earlier. Okay, now it wasn't a shock to us that the tangent plane at the top of the sphere ought to be horizontal, right? Because we're not morons. Yeah? Or at least most of us aren't.
Most, yeah.
Yeah.
I might be more on.
Right. Okay. Okay. But what is special about the top of the sphere in a sort of calculus sense?
It's the only place where the it's gonna be flat across.
Right. Okay. It's on this particular surface. It's the only place where the tangent plane is fully horizontal. Okay. Now, if we go back to Calc 1, we were interested in places where the tangent line was horizontal. Okay. Because what occurred at those places? First derivative. So what happened when your first derivative was 0 back in Calc 1? Right, you went through either maximum or minimum points, okay? Possibly, because there were the red herrings that inflection points that came in, right? Okay, so what we want to do is start to talk about the multivariable version of optimization, right? Optimization is the art of looking for local maxes and local mins, and being able to sort out the difference between a local max and a local min. Okay, does that make sense? All right, so for example, let me make a new function here. Oops. Okay, so I've made this surface here, and actually let me go 2 pi in both directions since I'm doing trig stuff. Okay, so this is our little egg crate surface, right? Okay, so, and actually, let me just do negative pi to pi. I think we get the idea. We don't need so many peaks and valleys. Okay, so what do I got? I got a valley, and I don't know why it does that. I got a valley down here and a peak up here. Okay, how do I know that there's a peak there if I didn't have this graph in front of me? Well, what should occur at the peaks and at the valleys? They should be places where the tangent planes are horizontal, right? Which means that the slopes that cooked up the tangent planes were both needed to be both 0, correct? Okay, so what is it called if I take my two derivatives, the derivative with respect to x and the derivative with respect to y, and I put them together in a vector? What did we call that thing? The gradient, okay? So what I'm looking for is when the gradient is 0, comma 0, okay? And the gradient is sort of our analog of the first derivative. In Calc 1, you found the possible locations of peaks and valleys, maxes and mins, by setting the derivative equal to 0 and then doing some algebra, right? Same thing here. We want to find points on surfaces that have both derivatives 0, okay? So let's start by doing that for our particular function here. All right, so let me go back to the iPad for a moment. Okay. All right, so what was my surface? I picked z, oops, z equals sine x cos y, right? I just kind of picked that at random. Okay, so what are the two partial derivatives here? So let me actually call this g. So what's gx? Cos x cos y. Okay, good. And what's gy? Negative sine x sine y. Okay. Okay, so what I'm curious about, and therefore, sorry, the gradient of G is the vector that has those two things as its coordinates. Okay, so the gradient just means stack them together and do a vector, nothing fancy. Okay, Gucci? Okay, so what I'm interested in is I want to find values of x and y that make the gradient equal to 0, 0. Okay, so it's not enough for me to find a place where the first derivative is 0 with respect to one variable. I want them both to be 0 at the same places. Okay, all right, now in this case, because I picked a function that's sort of trigonometric, how many answers are there to this question? Yeah, there's infinitely many, right? Because we could just keep adding 2 pi and the same stuff would happen. Okay, but let's find sort of an initial solution. Well, okay, what do you guys think a solution's going to be? We need something that makes cosine of x or cosine of y equal to 0, and something else that makes sine of x or sine of y equal to 0. What makes cosine equal to 0? When x is pi over 2, okay? So let's let x equals pi over 2, and then when is sine of y equal to 0? 0 would be a good one. Okay, so that's one solution. There are certainly many, many more, right? Because I could keep adding 2 pi. I could also think about negatives. Here I could have done 0 comma pi halves. That would have worked also, right? And so, yeah, so there's a crap ton of solutions that we could come up with, but this one is sort of an initial solution that we can concentrate on, okay? Okay, so what we have done is we've said at that point, the gradient is 0, which means at that point, the tangent plane is horizontal. Okay, but in Calc 1, if the first derivative was equal to 0, what did you know? Did you know that you were at a max or a min? Not necessarily, because what else could have happened? You could have been at a saddle point, right? So what did you do in Calc 1 to determine whether or not you were at a max, a min, or a saddle, or a point of inflection? What did you have to do? There were two different ways to do it. Huh? You could look at the concavity, right? So that's the second derivative test. Or you could have looked at the first derivative to see, did it go from positive to negative? That meant you went through a max. Or negative to positive, that meant what you meant through a min. And if it went positive, 0, positive, that was a point of inflection. Okay? So you could have either looked at the first or the second derivatives to sort out whether or not you had a max or a min. Okay. In the multivariable context, we're going to look at the second derivatives. Okay, that's the trick we're going to use. Okay, what's the problem, though, with the second derivative in a multivariable context? That we have multiple of them, right? How many second derivatives are there? There's 3 or 4, depending on how you want to count, right? Okay, 3 because the two mixed partials are the same, and yeah. So what we need to do is we need to sort out what is the sort of analog of the second derivative that we're going to look at and say positive, negative, 0, what's going on, okay? So I'll write this up and define it, and then we'll talk about the details of what it means on Monday and how we look at it, okay? So this thing we need to look at well, actually, let me write it this way. Okay, this quantity. And I'm going to call this quantity, well, actually, you know what? Let me call it, just let me be consistent with the book, delta. Okay. Now, how many of you guys, when you were in like Algebra 2, did anything with matrices?
Oh yeah,
Yeah?
like the box.
Yeah. Okay. So, grid of numbers, right? What I've actually done here, oops. Okay, so what I've actually done here is I've formed a matrix that has 4 entries, and then I've taken its determinant. Do you guys remember that, seeing that in high school, determinants?
Yeah, I'm not sure really.
Okay, but just take my word for it. The quantity that we're going to look at is that delta. Okay, so it's the second with respect to x times the second with respect to y minus the mixed one squared. And the reason it's squared is because, well, the two mixed ones are the same. So if I multiply them by each other, it's really squaring something. Okay. And then what we're going to need to consider is whether or not this quantity is positive, negative, zero, all of those sorts of things, like we did in Calc 1. Okay, now it'll work out a little bit differently than it did in Calc 1. What goes with max and min and so on, right? So we've got a little bit more work to do, and it's a little bit more complicated than the Calc 1 version, but that's sort of the idea, right? We're analogizing upwards, and this thing is going to be the tool that we use to try and suss out who's a max, who's a min, and who's neither, which we'll call a saddle. Okay, and the reason we'll call it a saddle is because, well, it'll look like a horse saddle, and I happen to have one over here. Not a horse saddle, but something that's sort of vaguely horse saddle shaped, right? So this point, the gradient would be 0, but it's a local min in this direction and a local max in that direction. So it's like a horse saddle, right? I could be like, giddy up, yeehaw. Yeah, I could. Or or I could not, right? Okay. But does that kind of make sense? Right? Or maybe this is more fun. It kind of looks like a Pringle chip, you know? Yeah. You like Pringles? Are they chips or are they huh? I don't know. Okay. So, right. So we need to be able to suss out, and we'll do it by considering this quantity and the things that make it up as to whether or not we have a max point, we have a min point, or we have a saddle point. Okay, or something completely different that sort of we have no idea what we've got. Okay, so there is a really interesting surface that I'll show you guys that's called the monkey saddle, because you know how that surface or a regular saddle, like it has sort of 2 dips, right? One for each leg. Well, there's a version of that that has 3 dips, right? And so if I were a monkey and I needed a horse saddle, as monkeys do, right, I'd need 2 dips, one for each leg, and then a third dip at the back for my tail. Yeah. The surface, that surface we call the monkey saddle.
Really?
Yeah, we're real clever mathematicians like.
Have you seen the Pringles concept can where they have like a twist at the bottom, so like it comes to the top, so you don't have to just reach your entire arm out?
You mean like they've realized that we've had the twist thing on deodorant for however many years, and so why not do that on a Pringles can also? Well, that works too, right? Because well, yeah, I mean, right? Once you pop, you can't stop,
It's over.
right?
I think there's like sprinkles of cocaine in those Doritos.
Yeah. Okay. All right, so does that kind of make sense where we're going to go, right? Is we've identified here a critical point. It was a point that made the gradient 0, 0. And then we want to classify these points to suss out, like I said, who's a max, who's a min, who's a saddle, who is just something completely different. Okay, and that's what we'll start talking about first thing on Monday.
There's something else.
Yeah, semester's not over yet, bro.
Huh?
Semester's not over
No,
yet.
I mean, like, you said, like, it's either max, min, or saddle. Like, what other option is there?
Oh, inconclusive, I guess, would be, you know, sort of thing. Yeah,
That's the only other option.
basically, yes. Well, okay, look, if you want to do this stuff properly, you need to take Math 225.
No, that's
Okay, for two reasons. One, you have an entire semester to do nothing but multivariable calculus. Okay, and two,
okay. I'll do my grade.
Math 225 comes after Math 223. So first you study linear algebra and matrices and stuff like that. And what that means is that when you do Math 225, you have all the tools from linear algebra to do this stuff properly. Okay. In two variables, we don't need all the tools from linear algebra. But three and more variables, we do need the tools of linear algebra, and that's why we do the courses in the order that they are. So think of the end of this semester as being an amuse-bouche for Math 225. Okay, yeah. So amuse-bouche, do you guys know what this means? Mouth amusement, literally. It's like if you go to a fancy French restaurant and you get just a tiny morsel of something to taste, it's before your appetizer, which in French is called an entree, the entry to the meal. I don't know why in English we call the entree the main course, because we're silly. Exactly. Okay. Anyway, yeah.
Does that work apply to four people that are holding the tray? Or like Costco?
Yes, a sample at Costco would be an amuse-bouche. Okay.
ASMR stands for autonomous sensory meridian response. So it's not like tingle down the middle of your back. You can't control when you hear something really nice.
Okay.
It's like,
Yeah. All right. Well, let's quit the stream. Have a fantastic weekend.